wondering, like, I don't think Discord do have recording.
Yeah, there isn't recording here. I usually just do it with OBS on my own.
You're gonna do recording on your other side?
Yeah. I always do that. I don't really use the Google Meet recording after all, so I just record myself.
Mm, right. I was wondering, like, if I could use snipping tool for recording, would that be sufficient, or do I have to download a third-party application for that?
What do you mean?
You know the snipping tool in Windows?
Oh, really?
Oh, you're using Mac.
Yeah,
Okay,
I'm using
sorry.
Mac. Yeah.
Yeah, I just noticed that.
Hey, Gabriel, you're here.
Oh, hello. Hello.
Hello.
Hello.
Okay, yeah, we'll have a
Hey
few
guys.
guys just joining. Who is this? Unboxing. This is Bartosz.
Yeah, it's Bartosz.
Okay, everyone start showing their weird parts by showing up on the internet.
Um,
Okay, I guess we can start then. Those are enough people.
okay. Wait, let me just.
Yeah, you might want to share your screen.
You should be able to see now. Yeah.
No. No.
No.
Yeah, I didn't say it. Hey, okay, yeah, I think he has. He has. Sorry. Loading. Yeah, it's there. Good.
Okay. Um. So, last time we kind of discussed how agents work and stuff, and this chapter is about problems when the agent doesn't have like an immediate solution, and this exact chapter, we're gonna talk about informed searches, and yeah, that's basically it. So when most of the environment is unknown, the agent has to formulate some kind of a goal or something, or like okay, let's start with have during the math class, the professor explained what state spaces are. Basically, you a certain environment, if you have a certain state, the state space is basically the all the different the whole graph of all the different states, and what we want to do is basically take an abstract version of that state space that's relevant to our problem and try to find a goal that suits our needs. So the way that happens, we start with a goal formulation where we pick a goal state. We have also the initial state, which is the state we start from, and we then want to formulate kind of like the relevant graph and start some kind of search to find a suitable solution for our execution. Let's say in this picture, I don't know if you can see my mouse. Can you?
Yeah, we can see your mouse.
Hello?
Yeah,
Yeah, I'm sorry, I'm muted. Yeah,
we're with you. We're with you.
yeah, we can see you. We can see you.
Okay, if you can see my mouse, then let's say we start from there and want to end at 40. Then we want to perform some kind of search. So we find a solution that's suitable to us. So basically, that's what the search does, and after we get that solution, we execute it. So I kind of jumped over here, didn't exactly follow the structure, but besides the state base and the initial state and the goal states, I should probably mention you can have multiple goal states. For example, in the game of chess, if you want to, like, your goal state would be any state that that's checkmating the opponent's king. So you can have multiple goal states. It doesn't need to be one. The actions is basically any action you can take. Like you have a function that takes the current state and returns a set of all the available actions you can take. And we have a transition model which just gets an action and a state and returns the new state. So basically, you just want to see the result of your action. Yeah. And the cost function, which is pretty important for writing a good search, is basically anything you define as the cost to transition from one state to another. So, or to execute any action. So, like, let's say from, like here in the example, to move from Sibiu to Pagaros, we can say our action cost is 99, I guess miles in this case. But basically, the action cost is used to see what it takes to execute any action in our set of actions. Yeah. The solution is basically a sequence of actions to a goal state from the initial state. So we kind of form a path in the graph. Here I wanted to talk about the abstraction as well. So when you have your relevant graph, I mean, okay, when you have the state space and you want to form the a relevant graph for your solution, you usually have to resort to some kind of abstraction, because if you get super specific, like let's say an action is moving to the left like a centimeter or something like that. If you make a state space with all of those small actions, it's going to take a really long time to search through them. So we usually resort to some kind of abstractions to make it way easier. Moving to example problems, I think I explained everything in 3.1. About the optimal solutions, we can also, like, a solution doesn't necessarily have to be the optimal one. A lot of the search algorithms actually do not always resort to finding the optimal solution. They just look for a sufficient one. Okay. The first example problem here that's mentioned is an example we saw in chapter 2 with the vacuum cleaner and the sucking of the dirt from the floor. So is it just okay? So basically, we have kind of like a grid that's basically in this case, it's mentioned like a grid world. That's like a 2D array of all the grids where anything can be placed, yeah? So basically, this would be our state space graph in our question. In our example, we have the vacuum cleaner here in the left grid with dirt on both of them. And here we can see if he decides to take an action to move left, he's just gonna end up in the same grid because he can no longer move left. And if he decides to move right, he will transition to this state where he's in the right grid, but nothing besides his position changed. Instead, if he decides to suck, he will remove the dirt from the left grid, or the same thing in the right grid if he did it after he moved to the right. And if he continues that, eventually he'll reach one of the goal states where everything is cleaned. That is the goal state in this case. We have okay, so here the actions is about it's like either move left, move right, or suck. But in the transition model, we have more like what actually happens in every transition. So if an action is just to do something, the transition model would be what happens when you move from a state to a different state, yeah? And the action cost here is just one, because you just perform one thing and that's it. You don't really do anything complicated or have to measure anything. You just move one state, yeah. The next example is of the Sokuban puzzle, which basically you have some kind of grid with numbers inside, and you have to place them in a sorted order. So in this case, you can see there can be lots of initial states, like this can be scrambled in any kind of way, but the goal state is exactly one. So so the amount of actions you can take also to reach the goal state also goes up by increasing the grid, which would complicate the state space and the whole search, and that's kind of what you have for the problem. For the action cost, we have it as one again, because it's just moving a tile one place. We don't have anything special happening, so we don't really need a big action cost or a special one. And yeah. The next question is a mathematical one, which is you have an initial number, and you want to turn the initial number into another number using any kind of operator from square root, Florin, and factorials. So basically we have also this has to be a positive number, yeah. So we have again the initial state being 4. The actions are any of the mentioned above. You can either square root it, floor it, or apply a factorial operation. and our goal state is getting this positive integer. So the thing is, we don't really know exactly how long it's gonna take. So we just search for anything that gets close to this. Yeah. So I guess moving to more real world examples. I guess, okay, the most common one you hear is the traveling salesman problem, which is just touring through every city on a given map, and yeah, you need to like, this problem has been, like, people have been trying to optimize it for quite a long time, but again, you can apply the same thing for any real world problem. You have the initial state, which would be the current position you start on. The actions, like, would be visiting any nearby city, or depends on the level of abstraction you want to apply, but usually something like that. Then you have the transition model, which would be the transition from your current state to the new one, and the goal state would be getting back to your initial position after traversing through all of them. Or yeah, and here we have the VOSI layout problem, which is basically you have a chip and you want to lay out cells with channel routing in a way so that you can minimize the area and circuit delays and just optimize it as much as you can. So again, we can apply this. The initial state would be just the like okay, you have the initial state would be the starting point of your channel routing, and then the goal state would be some kind of final position, yeah. And yeah, moving to robot navigation, similar to our any other to our routing problem with the traveling salesman. Robot navigation is basically you have any kind of robot and you can move it around, and you have the state space kind of be dependent on the actions it can take. So usually it's two-dimensional, but it kind of depends on how it's made. But yeah, and we at the end we have automatic assembly sequencing, which is basically a robot assembling parts of an object and finding some kind of sequence to optimize it. I mean, I guess that's all the important stuff you want to mention. Yeah.
Let me think.
Thank you very much, Vector. It was awesome.
Yeah.
Okay, great. I'm trying to share my screen right now.
Loading. Yeah,
Okay.
it's up. It's up.
And confirm that it's visible. Okay, great. Okay. Now we're gonna move to the search algorithms. Just gotta start the recording from my side, just in case. Okay. So now we're gonna start talking about search algorithms. So first we gotta define what is a search algorithm. So first of all, search algorithm is like a kind of a machine that you give it a certain problem and it spits out a solution. And that solution could be a binary state, whether this algorithm have found a solution or not, or it can be the solution itself. Okay. As we discussed earlier, that we have a state space problem, like you can get a map of some sort of cities connected to each other, and between each city there is a connection, sort of like a path that you can take between a city and the other one. And each path could be labeled with a cost, with certain cost or certain weight, where some paths are longer and more costly than the others. And in the first part of search algorithms, we have to discuss something that would help us execute the search algorithm, which is how to convert a state space into a tree structure. So basically, in search algorithms, you find it convenient to deal with trees and branches rather than just state space, because like trees are like more of a structure that a code can understand. So let's just discuss how can we transform this state space form into a tree-based form. Okay, so let's just say that we want to go from this city, Arad, to Bucharest. And those are the cities of Romania, by the way. So let's say we have decided to start and make Arad our root point. Okay, now that will lead to Arad expand to 3 different cities. And those cities are the neighboring cities to Arad. So we've got Zerend, Timizora, and Sibiu. So those cities are the cities that are connected to Arad, and those are the only options we can go to next. So let's say we have decided to go to Sibiu after that. Okay. Now in the tree, you can find that Sibiu has been expanded to its own neighboring cities. Okay. So let's just define some terms here. When we expand the node, we get something called frontier. So those neighboring cities or those nodes that has been expanded from their parent node are called frontiers. And each frontier or each node in that frontier is called a child. So we have a parent node, and that parent node have some childs or some children. Sorry. So we were discussing that. Okay, we have traveled from Arad to CPU, and we have expanded CPU. Okay, now CPU has 4 different neighboring nodes. And you can notice one thing, that one of those nodes is Arad, which is its own parent city, or the city that we have just previously visited. And one thing in search algorithms that you might fall into, like one of the traps, that you can visit a city or go to a certain state that you have already covered. So that would lead to the inefficiencies of the algorithm, and that is something that you have to definitely take care of. And let's say we just decided to go to another city after that. Let's just pick this city. So what is going to happen is that this city is going to expand to its own neighboring nodes. And again, one of the neighboring nodes is its own parent city. And then let's just move on and choose the next one, and then the next one until we reach Bucharest. Now we have expanded Bucharest to its 4 neighboring cities. We can say that, okay, we have finished our algorithm, or the algorithm has succeeded in its goal. So the algorithm can return, okay, I have found what we've been looking for. Now you can ask the algorithm one more question. Okay, so what is the exact path? What is the exact path that I should take to reach to the certain goal that I have just defined? Okay, so you can notice that a tree, or a node in a tree, when it's expanded, it can have multiple children. But one awesome property about that each child has only one parent node. So what we're going to do to just learn the path to go to Bucharest is we're going to do something called backtracking. So we're going to backtrack, or go back from Bucharest to its parent, and then go back from that parent to its own parent, and then so forth until we reach the root node. So backtracking allows us to learn the path that we should take to reach our certain state. And that is one of the great properties of search trees, that each node has exactly one parent node, which allows us to do that backtracking. One other thing to discuss is the projection of the tree on the state space itself. You can see that the nodes that we have just visited are colored with a different color, and those nodes that have been expanded in the tree. Okay, you can also notice that the tree is not fully expanded, like some nodes are not expanded, because this is how a code do visualize the search problem. Okay, so a code doesn't know what other nodes, or he doesn't expect what he's gonna see next. So he just like blindly opens the door and then sees what he's gonna meet after that. And then after reaching a certain goal, as we just discussed earlier, after we expand the certain state that we wanted to reach, we just do the backtracking to find out the path to our goal from the root node or starting state. Okay, so any questions so far about state space to tree conversion?
Did you talk about how can we prevent visiting the same cities yet?
No, just like in the implementation of certain algorithms, we're going to talk about how we do prevent like repeating visiting a certain city.
Okay.
So now so far seems all good. Okay. So in this chapter, we're going to talk about search algorithms. And in talking about search algorithm, or in talking about any algorithm, we're going to discuss the pros and cons of that algorithm. And talking about pros and cons, we're going to discuss what are performance measures that we can use to discuss or to evaluate that algorithm. Okay. So in this chapter, we will discuss like 4 different or 5 different performance measures. So first one is completeness. we gotta ask ourselves, like, is that algorithm a complete algorithm or not? So what is a complete algorithm? A complete algorithm is an algorithm that is guaranteed to cover every state in the state space we have. So if that algorithm is guaranteed to cover every state in the state space, we can call that algorithm is complete, and we can guarantee that we're going to find a solution using that algorithm. Okay. So the other metric that we can use to discuss performance is cost optimality. Okay, so does that algorithm optimize for cost? Does that algorithm account for the cost of different paths or different actions that it takes to pick the action with the lowest cost or not? Because most algorithm doesn't do that. The third metric is time complexity. Okay, so how much time does this algorithm take comparing to other algorithms? So the algorithm takes time merely in seconds, which is basically the unit of time. And that time would basically depend on the number of states an algorithm can discover. Okay, so the more states we have in our problem or in our state space, obviously the more time this algorithm can take. And then we have the space complexity. That's another metric to define. Space complexity is like time complexity, but it just discusses how much memory that algorithm would take in solving that problem. Okay, so memory is a crucial part in computer science because when you're like doing an algorithm, you are discovering a path in a search algorithm, and you would have to store some data about the things that you have discovered. And when it comes to storing data, a computer can only store so much until you run out of memory. So storing data, you'd have to be very careful with it because like it might run into a serious problem of running out of your computer memory. And then we have the problem difficulty. That's another metric to measure the difficulty of the problem itself. Okay, so we have two different types of problems. Okay, we have explicitly defined type and implicitly defined type. So explicitly defined type is a problem that we can just look at it and just see the whole picture, basically. And it can be represented by a state space graph. That's actually another name of it. So an explicitly defined problem do have vertices, which are the nodes or the states, and do have edges, where edges are like actions that you can take from a certain vertex to the other, or from a certain state to the other. And implicitly defined problems are like problems that you cannot draw a map of, where basically you have an initial state and you don't know what is the next state is gonna be unless you apply the action or have a certain transition model that takes you from a certain state to the other. And an example to make that clear is the Rubik's Cube. Okay, you cannot model every state for a Rubik's Cube, but you can know the next state when you apply a certain action by, for instance, flipping a side or a vertex. So yes, those were the problem measures. Any question on them?
No.
Okay, great. Next up. Okay, now we're gonna discuss our first algorithm. First algorithm is called depth first search algorithm, or in a short of DFS. So what is depth first algorithm and how it works? Okay, so depth first algorithm, from its name, it do discover depth. So it prioritizes the depth by going as far deep as possible into your search tree, and then backtracking each step to discover basically the other side of the tree. So let's just see how a depth algorithm or depth first algorithm is applied in action. Let's see you are starting from this node and just ignore the numbers, like they are just strings. Like you can just consider it as names of the node, like the cities, but they're just numbers. So they have basically no meaning at all. So let's say we are starting from the first node or the root node. Okay, now we have visited this node. Okay, after visiting the node, you expand and you find that, okay, now this node has two other nodes, two children nodes. Now there is two other nodes that I have to expand or I have to visit. Then you just choose one node of them. And then when you expand that node, you find out that you have two other nodes that you have to visit. And then when you expand another one, you find out that there is other two, and then you expand one. And then, okay, there is no other node to expand, and now you have reached the deepest point of the tree. What you're going to do then is you got to backtrack to its neighboring node, and then backtrack to the neighboring node of the parent node. And then you can keep going on with this structure until you cover your whole tree. Okay. Now you get your sequence of the tree by covering each node. And now we gotta ask ourselves the performance measure questions. Okay, so is this algorithm complete? So can any one of you tell me about that?
Yeah, it is complete because the state space is finite anyway.
Exactly. So this algorithm is complete apparently because we have covered all the nodes in our search tree. But there are some cases where this exact algorithm can be incomplete and can just stuck in the searching process forever. As you said, Alex, that okay, the state space is finite, but what if we have like an infinite part of the state space? What if we had like this path exactly just goes to infinity, and when you expand the node, you just find more and more nodes to expand? Okay, what is going to happen is that just the algorithm is going to go further and further deep into the algorithm until it reaches basically nothing, and then it will just basically run forever without returning the result. Okay? So that is one thing. Other performance measure. Okay, so what is the time complexity of that algorithm? Okay, so basically the time complexity of that algorithm is just the number of nodes or the number of leaf nodes that you have at the lowest level. So you can just notice that every level we go deep into, we just double the amount of nodes. Okay, so the first level has one node, the second level has two, third level has four, and the fourth level has 8. And a mathematical formula of that, you can just say that for this binary tree, we have 2 branches in every level, and those 2 branches are just doubled every time. So you're gonna 2 times 2 times 2 times 2 by the amount of levels that you have. So basically you have 2 to the power of the current level that you are on. So this algorithm has a complexity or a time complexity of 2 to the power of L. Or more generally, you can just say it's B to the power of L, where B is the amount of branches that you have for each node, and L is the levels or the deepest level that you have on your tree. Okay. So what is the space complexity of this algorithm? Well, one of the greatest advantages of this algorithm is that it does have very, very low space complexity. As we've noticed that we didn't keep track of all the tree, or we didn't keep track of much data of the tree. What we have done is like we are exploring a branch, okay, or we're exploring a node, and we just figure out that, okay, so we gotta remember that this node that we have just explored has two children nodes, okay? So each node we do expand, we just have to keep track of its own children nodes. So at the end, we are just exploring, or like we're just memorizing that like 3 extra nodes over the path that we've just took. And this algorithm is famous of having the lowest space complexity of all algorithms because you don't have to store much data about your search problem. Okay. Okay, great. So the space complexity of that algorithm is basically m, while m being the level that you have reached, multiplied by the number of branches. So basically, you just multiply q by how many levels that you have discovered. And that would lead to the big O of m, because we just take the greatest order, and it's just an order of the first power. Okay, so more levels you have, definitely the longer time it's gonna take, or the longer space that it's gonna take. So yeah, and to discuss the code implementation of this algorithm, you can use a very, very useful property of coding, which is something called recursion. And what allows you to use recursion in this algorithm is basically whenever you're going to start on that tree, you're going to just repeat the same process over and over again. So let's say if we started at node 20, you're just going to go to 40 and then go to 80 and then backtrack to 90. So basically you can just reapply the same function that you have chosen to apply in the first node, which is the root node, over and over again. So let's just read through the code real quick. So basically what we do is we take the first node, which is the root node, we give it to the algorithm or the function, and then we check if that node is visited. Okay, that node is visited. Sorry, we don't check, we just mark it as visited, okay? And then we just loop through its neighbors, okay? So we just see how many neighbors does this node have, and just like loop through all of them. And then just check if that neighbor is visited. If that neighbor is not visited, you just reapply the algorithm on that neighbor again. And one thing we should clarify in this example that we have disregarded the already visited nodes. Okay, so when I expand 20, I should get a 10, which is another neighboring node to 20 because they are basically connected. But what we have done here is like in that diagram, just to have more space on my screen, I've just disregarded this 10 and just went with the other unvisited neighbor nodes. So anyway, you don't just go and visit an already visited node. So what you're going to have to do is like you're going to have to keep track of the visited nodes, and you can do that by an array. That array, you would just store all your visited nodes in that. Okay, so any questions on that algorithm?
No.
All right. Okay. Next one. So next algorithm is called breadth first search algorithm, where you do prioritize the first or the breed of the node, okay? So from its name, what we're gonna do is basically we're gonna discover the levels of the tree one by one, okay? So we're gonna discover the first level, and then the second level, and then the third level, and then so on, so on, so on, until we reach the deepest part of the tree. Okay, so we're talking about, okay, we are discussing a certain level of the tree. So we have expanded a node, and we have multiple children nodes that we need to expand. So in that case, we have to keep track of the children node by storing them in a queue and then discovering them one by one. Okay, so in this case, in this algorithm exactly, we're gonna need a queue, which is just like a fancy term for an array. But like a queue is like has a special property where you have the first element that you insert in that queue, you'd have it to go first, which has a property called FIFO, which is first in, first out. We have other method of storing data, which is called a stack. So a stack is basically the opposite of the queue, where the last element you put in the stack is the first element you take out of the stack. So a queue can basically be like the queue for buying movie tickets, while a stack could be like you stacking like dishes on top of each other, because it doesn't matter which dish you're gonna take next because they are all basically the same. So okay, so let's see how do that breadth first algorithm works. So let's say we have the search tree, and again we are disregarding the already visited nodes, and we can say that by exploring the node that is number 5, we just disregarded the 10. So anyway, we're gonna have to keep that queue just right to our side to see what is going on. Okay, now we're gonna visit the root node. By visiting each node, you just like store that node into the queue, okay? And the next step is that you have to go to the queue and then take take the first thing, or the first thing that you have stored in that queue, and then dequeue it, take it out of the queue. And then after you take it out of the queue, you say, okay, that node is visited, and this is the first thing in my sequence. And when you visit this node, you just expand its children nodes. And by expanding its children nodes, you just put them again in the queue. And then after that, you go to the queue again and take the first element of the queue. And then, okay, this one is going to be the next in sequence. And then after you take that element, you got to expand it and just look at its like neighbors, okay, its children, and then put them as well in the queue. And then after that, you're gonna take the first element in the queue and then put it in your sequence. Okay. Now we have taken the last element, which is 15, and then we're gonna save its children in the queue. And then we're gonna look in the queue for one more time. Okay, we have node 3, and we gotta dequeue that, and now it's gonna appear in our sequence. And then we have to expand node 3. But like trying to expand node 3 would lead to no further nodes, because node 3 is just the deepest part in the algorithm, or the last node in that path. So we're gonna just go back to the queue again and just take 7 and put it in our sequence, and then try to expand 7. Okay, I think there. Just we have to take the next element in the queue, 12. Okay, expand 12, nothing there. Just I have to take 18, and voila, we have done our search sequence. Okay, and you've just noticed that we have went through each level one by one. Okay, so first we got 10, and then 5 and 15, which is the next level, and then 3, 7, 12, 18, which is basically the lowest level in the tree. So that's called breadth first algorithm because it basically explores the tree level by level. Okay, so what are the performance metrics of this algorithm? Is that algorithm complete? First of all, can anyone verify?
Sorry, what was the question?
Is that algorithm complete?
Is BFS complete in this graph?
Mm-hmm.
Yeah, it is because it's finite anyway. And you can just do every level.
Okay, so it's because it's finite is complete, but like, would it be complete if your space is infinite, basically?
You will also be complete because the algorithm, if like there's an answer in like a in like a distance that's limited, you will still be able to find it like
Exactly.
within that distance.
Exactly. Awesome. So that algorithm would be complete anyways, as long as there is an answer in your problem. Okay. So no matter your state space, is it infinite? Is it finite? As long as there is an answer in your state space, you're gonna guarantee that you're gonna find that answer. And another feature of that algorithm, it optimizes for the cost. Okay. So basically, you are discovering your tree level by level, which will guarantee that you are gonna reach your target state with the lowest level possible, right? So we can say that, okay, so this tree is cost optimistic, but under one condition. As we have seen that in that tree, we haven't regarded like a cost for every path. Okay, so we are basically like assuming that every path has the same cost in that tree. So that tree would be cost optimistic in just the case that all the paths in the tree just to align to have the same cost anyway. So what is the time complexity of that algorithm? So basically, the time complexity of that algorithm is like the previous one, where you'd have to just explore the deepest part of the tree, which is also b to the power of L, where L is the levels or the lowest level in the tree, and b is the amount of branches you have. So that is the time complexity of that algorithm. Okay. And yeah, by the way, the time complexity, we just take the highest order because all of that are considered in the time complexity, but they're just in lower orders, so we just do consider them as insignificant to be to the power of the highest order. So basically, we should just say that the time complexity is just the highest order of all of them. So yeah, so this is basically is the number of leaf nodes or the number of the deepest nodes in the tree. And what is the space complexity of that algorithm? In that algorithm, you just, as we have discovered, you keep track of all the nodes that are on the same level. Okay, so how much node do a certain level possess? Well, it's also b to the power of d, where d is the level that you are on, or D is like the deepest level specifically, and B is the branch for each node, the number of branches for each node. So in our case here, like we have 2 branches, so B equals 2. And we have like some sort of a discussion where, like in a real world example, you can have a tree with like 10 branches, and like for each branch, and for the 10th level, when you go deep by 10, you would just have like 10 to the power of 10, which is like an insane number of nodes, which could be like needing in for like 10 terabytes of data. So this algorithm, we can see that it has very low space efficiency, and it needs like quite a lot of memory to be executed. So that's one downside of that algorithm. Okay, looking at the code. In this code, like you can just notice that there is no recursion. So what you're gonna do instead is just you're gonna do a while loop, and just you're gonna loop on like every part of the tree. Okay. So the while loop, it says, okay, so while the queue is not empty, while you are having like elements in your queue, you just have to keep going on and on. Okay. So basically, you'd have to start by like assigning a visited equal to true to the first node that you give to the tree. And then you just put that node in the queue, as we just did earlier in our visual example. And then you just loop through the queue, and just like take the first element in the queue that you have, okay? And then loop through its neighbors. And each neighbor you go to, you just check if it is visited or not, because like, as we said, we have disregarded already in that tree the already visited nodes, but like it doesn't mean that they're not going to appear in your algorithm. So in your algorithm, you just have to filter out the already visited node. And then when you visit the node, you just assign it as visited one, and then do append it to the queue. Or in other words, just like put it at the lowest part of the queue and at the end of the queue. It's just like you just keep doing this process again and again by like taking or extracting the first element and then looping through its children, and then checking if they're visited to assign them as visited. If they're not, and then just append them to the queue. So yeah, by that you can implement the BFS algorithm. Any questions on that? Okay. Seems all good. Okay. Moving to the next one, Dijkstra's algorithm, or also known as a uniform cost search algorithm. So in the last algorithm, we've discovered the breadth first algorithm, where we do where we do chase uniform depth or uniform breadth. In this one, we are chasing or hunting for uniform cost. Okay, so basically in this algorithm, you just try to optimize for the cost that you have on your graph. So as the first example that we have seen, where you have the cities of Romania, and between each city and its neighboring one, there is a specific cost for that path. Okay, and what algorithms do take into account the specific cost of each path? It would be the Dijkstra's algorithm that we're going to discuss. Okay, so let's jump into how this algorithm works. So let's say we have this chunk of the graph of the cities of Romania that we have seen in the beginning of the lecture. Okay, so our intended goal is to go from Sibiu to Bucharest. Okay, and each path has its own cost. Okay, so our goal is to go to Bucharest with the minimal cost possible. Okay, first of all, we're gonna start with Sibiu, obviously, because the root node, and then we're gonna expand that. Okay. Notice a couple of things here. When we expanded Sibiu, I forgot to introduce you to this data structure that we have here. Okay, so basically we do have like this table with like every city labeled in that table, and there is a cost value right beside each one, and there is adjacent to that the previous city or the parent city that this city have expanded from. So let's do it one more time. Okay. So we just expand the first one or go to the first one. So this is the root node. What is the cost of the first city? It's basically 0 because this is the city that you started from. So we're going to assign 0 to the cost value of the first city. And then we just don't have a parent city for the root node. So we're just not going to assign anything. And then we just have to expand that city into like its neighboring city, and we find that okay, there is 2 neighboring city for that one, and each one has its own cost. Then you'd have to update these values in your data structure. You have okay, the city RV have 80 as a cost. You can just consider it as 80 minutes to go to that city, and its parent city is just Sibiu, the last one we just visited. And then we have Fagras, the next one with 99 cost. Okay. Next, we're going to have to ask ourselves, okay, what node should we expand next? What city should we discover next? The algorithm says, okay, so the rules is always to expand the city with the lowest cost ever, okay? So to go to RV, the city, from Sibiu, you just take 80 minutes. And to go to Fagras from Sibiu, you take 99 minutes. So obviously, RV is the lowest cost city. So this is what we're going to expand next. Okay. Notice like we didn't disregard the already visited one because there's a point here. Okay. So we just expanded RV. Now we have Sibiu, like you can go back literally to Sibiu in 160 minutes. And 160 minutes is basically the time that you're going to take to go from Sibiu to RV back to Sibiu again, which is basically the cost of travel between Sibiu to RV multiplied times 2. And this one is the 177 is the cost to go actually from Sibiu to PTT. Okay, so if I do pronounce it correctly, so the cost to go from Sibiu to PTT is 177, which is basically the cost to go from Sibiu to RV and then from RV to PTT, which is 80 plus 97. Okay. And we're going to do is like, okay, we have to update those values into the data structure. And we're going to see that, okay, Sibiu has 160. So we're gonna put that into data structure, and then we get stumbled across that. Okay, Sibiu has 0. It already has a value, right? And that value is already lower than the value we've just got, right? So the algorithm says, okay, if an algorithm do have a value already, you shall not, or if an algorithm, if a node do have a value already, okay, and that value is lower than the value you've just discovered, don't update that value. Okay, so CPU has already 0, and 0 is obviously lower than 160, so we're not gonna update CPU. And then we're gonna look at PDC. PDC did have infinity at the beginning, because like in the beginning, I forgot to tell you that we assigned the cost of each city to infinity, right? So we just like discovered that you can go to PDC in 177 minutes from CPU. So we're gonna update that. Okay, just say that its parent city is RV. And then we've got Fragrance with 99. Okay, the next thing is to go to the city with the lowest cost. Okay, so what options do we have? We have CPU 160, we have PDC 177, and we have Fragrance with 99. So obviously we have the lowest cost of the city is Fragrance. So that's the city we're gonna discover next. Okay, so discovering Fragrance, we know that, okay, we have achieved Sibiu again, right? And then we have Bucharest, which is the target city that we need to go to. Okay. Now we have discovered these like 3 cities, Sibiu, RV, and Fagras, because those are the cities that we have expanded. The other ones we just didn't expand yet. So we have PDST, Bucharest, they are not expanded. So they are not considered as discovered. But we've just had an information about the cost to go to them. Okay, and basically this cost is the number to go to them from the parent city or the root city that we have started from. Okay, now we had like previously Bucharest at a cost of infinity, so we've just like discovered that it could be we could arrive to it in 310 minutes, so we have to just like update that. Okay, so is the algorithm done now? Okay, so the algorithm says you shall not be done until you expand your goal city. Okay, so although we have seen Bucharest appear on our search tree, but the fact that we just didn't expand it yet makes us, okay, we have to carry on because we haven't reached our goal city yet because it's not expanded. So next on the list is the lowest cost that we have, or the lowest cost that we can expand. So the lowest cost here, obviously, is PDST, because CPU is already visited. So we just discard that. Okay, we don't want to go to already visit this city. We just go to the lowest cost or the lowest unvisited city in terms of cost. Okay, so we're going to expand PDST. And then by expanded PDST, you just discover, okay, we have RV and Bucharest, RV at 274, and then we just check, okay, RV here is 80, so there is no need to update that. We have Bucharest at 275. It was previously 310, so we have to update Bucharest, okay? So because this value is lower than the value that was written in the data structure. Okay, so next on is we'd have to expand the next unvisited city. So RV is already visited, Bucharest is not visited, and Bucharest also is not visited. And which one should I expand next is basically the one with the lower cost, which is this one right here. So by expanding it, you can see that it turned red and we have just visited Bucharest with the lowest cost possible. Okay, so you go to have a look to that data structure that you have, and you see, okay, so Bucharest, you can go to Bucharest with 278 minutes of cost. And this is guaranteed to be the lowest cost for going to that city from the chosen parent city. Okay, now we've got the lowest code basically to go to every city in our data structure, or the every city in our state space graph. And we have just to figure out something else. Okay, what is the exact path to go to that city from that data structure? Okay, so the algorithm says, okay, if you want to find the path to go to your current city, you just go to the current city in your data structure and then just observe its parent city. And then do that recursively until you reach your starting point. So what is the parent city of Bucharest? Okay, it's Pitosti. What is the parent city of Pitosti? It's Bucharest. I think there's something wrong in that. But anyway, shouldn't have updated in that manner. I don't know if I pressed on something else, but like the parent city of Bucharest should be Pitosti and then RV, and then you just go to Sibiu. I think there is a certain bug in that software that I haven't discovered, but anyways. Let's just understand the code of that. Okay. So, before just we go to the code, like, does anyone have any question about that? Do we still have people in that call, even?
No, no problem.
Okay.
Yeah.
Okay, awesome. Okay, let's talk about the code, or how to implement that algorithm in terms of code. Okay, so basically you'd have to identify your data structure, which is like every node should have a cost of infinity in the start, and then you just assign the distance of 0, or like the cost of 0, to just the first node, because that's which you started on. And then you would have to make something called a priority queue. Priority queue is different from a queue, because a priority queue, you don't just take the first element that you inserted in the queue first, but like you take the lowest element in your queue in terms of the cost. Okay, so that is priority queue. You do prioritize the cost over the level, or the arrangement of the elements in your queue. So we just loop through every element. We just see the current distance and current node of the minimum cost node that we have. And then we just like see if that distance is greater than the already found distance in the data structure. If the distance that we have just discovered is greater, then we just have to continue looping. We don't have to just update it. And if it's not greater, then you'd have to update that distance that we have just discovered. And then what you're going to do basically is just loop through its neighbors and update the distance based on the weight and the current distance that you have. And yeah, and basically, if you have found a shorter path than the distance that you already have, you'd have to update that in the priority queue, and append that in the priority queue with the newest cost. Okay, and priority queue is like thing that that allows you to extract the lowest cost element in it, in which it's gonna help you in that algorithm to just go, because like in that algorithm you just pick the lowest cost node to go to next. So you would have to just arrange them in terms of cost in your queue. Okay. So let's talk about the complexity of that algorithm. First of all, is that algorithm complete? Well, looks like that we have discovered every element in the trees, or in the end, we're gonna discover every element in a state space. So basically, we can just safely say that this algorithm is complete, and we can then discuss, okay, so what is the time complexity of that algorithm? So time complexity of that algorithm is a bit tricky. So you don't discover algorithm based on levels, but rather you do discover them based on cost. Okay. So C here is the cost of the path that you should take, or the cost of the optimal path that you should take to your solution. And like epsilon here that we have is the smallest cost possible in your state space. So in our state space here, like we can see that the lowest cost possible is 80. So the maximum amount of steps that you can go, or the maximum amount of levels that you can go to your desired goal would be like the cost of your goal divided by the minimum cost that you can have. So this would be the maximum levels that you can go, and this is the amount of branches, which is usually, in this case, it's just like 2, because like each branch has like basically 2 elements. And yeah, so you just raise the branch number to that number, and we just add 1 here. Like why is this 1 added? So basically we have discovered that, okay, we had to expand the branch, or we had to expand the node that we have just visited to say, okay, we have reached our target. So since we do expand the node, that means that you do discover 1 extra level, so you're gonna have to add that 1 to your complexity. And the space complexity basically is the same number, because you just do store like data about all the cities that you just expanded. So basically every city that you're going to expand is you're just going to store it into your data structure. So definitely have the same space complexity. And yeah, one other question is that algorithm cost optimistic, or does that algorithm optimize for the cost? Definitely, because like this is what is defined for. So yes, do we have any questions?
No.
No. Okay, great. Next up, we're going to discover something called iterative deepening search. When we discussed the first problem of depth first search, we have discovered an issue in that algorithm, that this algorithm do get stuck in infinite state spaces. When you have an infinite space, your just algorithm is gonna run forever. So to address this problem, we can introduce a concept called iterative deepening search, where you'll have to basically apply the DFS algorithm iteratively, and each time or each iteration, you just expand the depth by 1. Okay, so you just limit the depth the algorithm can go to. For instance, you can say, okay, so the algorithm will go to depth of 2 in the beginning. If it didn't find a solution, so go to depth of 3. If you didn't find a solution, go to depth of 4, and so on until you just basically do find the solution that you have been looking for. And one of the things that it can appear that this approach is very inconvenient and very inefficient, because you do just basically repeat previous tasks and just like do visit nodes that have been already visited multiple of times. But the argument here is like it doesn't differ so much. Okay, so the nodes that you do visit multiple times are basically nodes in lower levels, and the lower level you have, the more repeatness that you're gonna take to or the more times you're gonna visit that node in that lower level, and the higher level you have, the less amount of times you're gonna visit that node. So the argument here is like we're just discussing that the time complexity is based on the highest level, right? Or the lowest depth that we can reach. So this is the highest order of magnitude that we get. So basically we can neglect all that, and the time complexity of that algorithm would basically be the same as the time complexity of the depth first search, without any difference, like without much difference. And there is a comparison between the iterative depth search and the BFS. that we have right here, and you can just see that they are in the same order of magnitude. Definitely the IDS is slightly bigger, but it's bigger in lower orders of magnitude, but like the highest or the most significant digit is basically the same. So yeah, that is the iterative deepening search.
Hmm.
You have a question?
No, it's fine.
Okay.
It's good.
Okay. Next on the list is bidirectional search. This is not an algorithm in particular, but it is like an implementation method of different algorithms, where basically it's like you can implement any algorithm, but what you're gonna do is you're gonna have like two starting points. One starting point would be the point that you choose to start from, and the other starting point would be the point that you are intended to reach, or the goal state, right? So basically what you're gonna do is just like you can apply any sort of algorithm, if it's like BFS, whatever it is, but you're gonna like do it from both directions. And the end state, or the thing that is, or the condition that would tell you, okay, so the algorithm have found its intended path, is when these two paths do meet in the middle, right? So when you're starting from a certain point and other certain point, and you're searching for your partner, you just meet at a middle location. And when you do meet, you're just, okay, so we have discovered our path. So the first partner would say, okay, so my path was that way. The second partner would say, okay, so my path was that way, and unionizing that would give you the path that you should take. So the argument of that is like this algorithm would be much efficient, or like more efficient than other algorithms, that you don't have to discover like the exact depth of the previous algorithms. Okay, you just basically have to discover the half of the depth of the previous algorithm. So instead of going to depth d and having a time complexity to b to the power of d, you just have a time complexity to b to the power of d over 2. And for sure, that is multiplied by 2, because like you do cover the same depth twice, but definitely covering the same depth twice is much better than covering double the depth. Okay. So that was it. So any questions on that?
No, it's good. It's good.
Okay, great. Next up is a summary of all those algorithms that we have just discussed. So BFS is basically considered as complete, yes, if the space is finite. And like definitely if the space is finite, and even if space is not finite. We're talking about breadth. So even if space is not finite, you do consider this one as complete if there is a solution. So the optimal cost of that one, yes, it do optimize, but just under one condition: if all the costs of the paths is equal, and the time complexity is like exponential depending on the level, and the space complexity is equal to the time complexity. And yeah, similarly, we can see that the advantages of BFS is that it has like a lower space complexity, which is O to the M, and the algorithm that do just like optimize for costs is like, we do have our candidate here, like the uniform cost, and this is like unconditional, because you don't have if you don't have equal cost, it would gonna optimize for the cost anyway. So that is a summary that you can just look upon and just like memorize, or just refresh your memory on what we have just discussed. So yeah, I've done now. Anyone has any questions?
I don't have. Anyone else has?
I don't have any.
Okay, guys. So hope that was clear for you.
Right.
If you have discovered.
Mm-hmm.
In the next part of this chapter, we do discover, or like we talk about algorithms that are called informed search algorithms. So those algorithms were basically uninformed search algorithms, where you do just hard code the algorithm without basically giving it a knowledge about like the state space that you have. But like the next part, we're gonna discover like, okay, what knowledge can I give to the algorithm on the state space to be able to optimize its path further.
Mm-hmm. Mm-hmm.
So yeah.
Yeah. Okay. Okay. Just kudos to Hossam because I think your slides were done very well. I don't think any one of it had ever done something like that, so it was pretty good.
Thank you. I've actually like this one was like coding a code that I have did like in sort of a web application. So I'm gonna try to host it on like a hosting platform, and then I will send it to you guys once I'm done with that, because I just have to figure out how to do it in the first place.
I think you can just like export it as a PDF if you want. Like just use the how the print like a print feature of web browsers, and you just try to export the page. That might be easier.
Yeah, but it's
Yeah,
gonna lose its like interactivity. But
Yeah.
but I'm gonna do that
Pretty
if like
much.
if I struggled with hosting it, I'm gonna do that definitely.
Yeah. Okay. Okay. Okay.
you can also just like put it on Git and just link the repo, and everyone can run it locally. Yeah.
Yeah, I've thought about that. I'm gonna do that also. But the issue is like to run it, you'd have to download a couple of packages, and that could be like some pain in the ass for a couple of people.
Okay.
You
Okay.
can set up a Docker or something.
That's just a
Okay.
slide. Yeah. That sounds too much effort.
Yeah.
I'm gonna
Yeah.
discover all that awesome solution.
Sure, sure. Okay. Let me think about what's the next week because I think when I check the book, I think the second part of chapter 3, it's like it's like it's like about the equal amount of our thing, but when I read it, I think it also has certain complexity. So I think we're just gonna continue with the plan of having another group, finishing chapter 3 as we discussed. And I think the people, let me just check the list. The people I've assigned is gonna be Victor and Alex, which is me and Victor. Yeah. Just to make sure people knows. And then I've also briefly checked the rest of the book. Like briefly. I think regarding our current progress, I think we'll still be able to finish like half of the book in in the end of January or something. Of course, that had to depend on our time allocation because I know like when final term comes, you probably would read something else instead of the book. But I think we're on good track now. There's a few chapters in the book, like the logic sections. I think we can skip that very quickly. So I think if I went to the logic sections, my estimation is to combine all 3 chapters into a single week because it's just a bit too easy for us. We can just like try to brief it through. Yeah.
Okay, I do have a suggestion for like things that we can implement for like in our